All right, in this part of the unit, we are going to be focusing on solids. So we're going to move away from liquids for a minute, and we'll come back to it later, but we're going to talk about solids for a little while. And so there are many different types of solids, and all of them can fit into one of these categories. So I'm going to draw a little graphic organizer to sort of organize my thoughts before I go into the different types of solids. So you have this big category of solids, and you can break them up into two categories. You can break them up into crystalline, and you can break them up into amorphous. So a solid is either a crystalline solid or it's an amorphous solid. Now, if you have a crystalline solid, that can be broken down into further subcategories. And so there are three of them, and they can be broken into an ionic solid, a molecular solid, or an atomic solid. And then the atomic solid can be broken into three more subcategories. You have metallic, you have network solid, sometimes called network covalent. So I'll put the word covalent there in parentheses. And the last one is group 8A. Now, within the course of this unit, we're going to talk about all of these, and we'll spend the majority of time talking about these metallic solids and these network solids. We talked a lot about ionic and molecular solids in Chem 1, and amorphous solids I'll mention briefly in this video, but we're not going to go into too much detail about amorphous solid. That's not a big topic on the AP Chemistry exam. And so we're going to spend most of our time in this unit talking about metallic and network covalent solids, because they are the ones that, while they're very important, they are the ones that you probably know the least about based on your experience in Chem 1. All right, so if we start with the biggest categories, the crystalline solids and the amorphous solids. So first you need to know the difference between the two. Now, amorphous solids have a considerable amount of disorder in their structure. They have specific components, but they're not as ordered as a crystalline solid is. So a crystalline solid, in comparison, is arranged of highly organized components, and specifically they're in components called lattices, which I'll talk about on the next slide. Amorphous solids don't have that they don't have that organization or those lattices. And so, for example, glass is one of the most common types of amorphous solid. And so as it says here, that glass is a solution in which the components are frozen in place before they have achieved an ordered arrangement. And so while glass is a solid, so it has a rigid shape, there is a great deal of disorder to the structure, which is why if you have a stained glass window, for example, over time the glass particles will settle at the bottom, and that's just because they have a rigid shape, but because of the organization or the lack of organized arrangement, those particles can move around and they can arrange themselves in different ways because it doesn't have that highly ordered lattice structure like a crystalline solid does. Now, as I mentioned a moment ago, crystalline solids have these highly ordered components, which I said were called lattices. So what a lattice is a three-dimensional system of points designating the positions of the components. Now, the components can either be atoms, they can be ions, or they can be molecules based on what type of crystalline solid we're looking at. And if you then take that 3D lattice and you break it down into its smallest component is going to be called a unit cell. So the picture here on the left shows you what a unit cell is, and if you take this unit cell and you repeat it a bunch of times, that's how you get the lattice. Each of these points around a unit cell is called a lattice point. And so these lattice points can either be this unit cell could be an atom, it could be an ion, or it could be a molecule based on whether we're talking about atomic solids, ionic solids, or molecular solids, which is what we'll get into in a moment. But first I want to talk a little bit about this lattice and how we know exactly what the organization of a lattice structure is. And the way that scientists do that is with something called X-ray diffraction. And so this is sort of a depiction of what X-ray diffraction is used for, and so specifically it's used to determine the structure or the lattice of a crystalline structure. So it's used for determining the structure of a crystalline solids lattice. And so you don't need to know too much about this for the AP exam, but you do need to have some idea of how it works. And so if we take salt, for example, salt is something that we know is a crystalline solid. It has a very specific order. It has a defined lattice and defined lattice points. And so if they take some X-rays and shine them through a crystal of salt, it's going to go through this detector screen right here in gray, and then they're going to get some readout. This readout here is called the diffraction pattern, and it's going to be shown onto a screen. And the waves that it is looking at is depending upon the different types of interference that we look at, and we'll talk more about that when we look at atomic structure, the different types of waves and intensity and how that looks. And so don't focus too much of your attention on that right now, but on this diffraction screen right here, this diffraction pattern, this is basically what they focus on. And so if you were to focus on this and sort of flip it on its side and look at it in at a different angle, you're going to get something that looks like this. And so you have the solid, which is this part down here. That's what these dots are, your lattice points. And so you have the salt, and you're going to shine the X-rays through it. Those would be the incident rays, and they're going to hit the lattice points. Once they hit the lattice points, they're going to bounce off, and they're going to then become reflection rays. And that reflection rays is what's going to go hit the detector. And based on these measurements, you have a couple different things here. And so we specifically want to look at the distance here, this theta, that is going to be the angle of incidence and reflection. It's going to be the same. And so if something has an incident angle of 30 degrees, it's going to have a reflective angle of 30 degrees. That degree is not going to change at all. And so based on this equation, that's called the Bragg equation. Now you don't really have to know how it's derived. This is just the Bragg equation that we're going to be using, or the form of it that we're going to be using. And so using the Bragg equation, we can figure out a couple different things. You can figure out the angle of incidence and reflection, or more, not specifically, but more helpful, I would say, in determining really what the structure of this particular solid looks like is what D is. So D is the distance between the different layers in the crystalline solids, or the different unit cells. And so if I just put up here the different variables, so N stands for just an integer, and that's something that you're going to be given. It's not something that you need to memorize. Lambda, the next variable, is the wavelength of the X-rays hitting the crystal. Now that's something that the X-ray diffraction machine, the scientists would have to set the various wavelengths, and so that could be something that you are given or solving for. As I mentioned, D stands for the distance between the layers in the crystalline solid, and it's often measured in angstroms. And so that's a unit. An angstrom is 10 to the negative 10th meters, so it's pretty small. And then theta is the degree of incidence and reflection. Now it's important, because we're dealing with angles and degrees, that your calculator must be in degree mode to do these calculations. And I will remind you on the day of the test or for a quiz, but just as a reminder now, when you're dealing with the Bragg equation, you must have your calculator in degree mode. If it's in radian mode, you are not going to get the right answer. And so let's do an equation with the Bragg equation to kind of show you what it is that you could be solving for. So X-rays of wavelength 1.54 angstroms were used to analyze an aluminum crystal. A reflection was produced at 19.3 degrees. Assuming that the integer n is equal to 1, calculate the distance d between the planes of atoms producing this reflection. And so if we look at the Bragg equation, n times lambda is equal to 2d sine of theta. And so then if I just start plugging in the numbers that I am looking for. So you have our integer is 1. Now it's important to note with the wavelength and d, they must be in the same unit. And so if we have angstroms here for our wavelength unit, that means when we solve for d, we're going to get that in angstroms. If you were given the wavelength in nanometers, your distance is going to come out in nanometers. And so that's very important to know, especially if you're solving for something like theta, where you're given both the wavelength and the distance. You need to make sure that they are in the same unit. Now, because we're solving for the distance, the unit really isn't too important for right now. We know it's just going to come out in angstroms. And so that's integer times 1.54 angstroms is equal to 2 times distance that we're solving for times the sine of 19.3 degrees. Now, making sure that my calculator is in degree mode, I can do some math and figure out that the distance between the layers in this aluminum crystal are 2.33 angstroms. And that would be the answer to the question and how the Bragg equation is used. Now remember that, for example, if I was going to change this question a little bit, and let's say that I didn't give you this and I told you that your distance was, let's just use the numbers that we already know. So we know that the distance between the aluminum crystals is 2.33 angstroms, but we want to know what the angle of incidence and reflection would be. And so if I just then plug in the numbers that that were given, and so integer is 1, wavelength is 1.54 angstroms is equal to 2 times 2.33 angstroms times the sine of theta. Now this I am just showing you to remind you all how you solve for theta. So you take 2.33 times 2, and then you would do 1.54 divided by the 4.66, and so you end up getting 0.330 is equal to sine of theta. Now remember, if you haven't used trig functions in a while, that if you want to figure out what theta is equal to, you're going to take the inverse of both sides. And so on your calculator, it's going to have a little inverse, a little sign to the -1 power of 0.330. And when you do that, you should in fact get about 19.3 degrees, which gets you back to what it is that we know from the question. So that's just a reminder about solving for theta for those of you that haven't used your trig functions in a while. You're going to solve like you normally would, and then you're left with the sine of theta, and to figure out what theta is, you just take the inverse sine of both sides. And in the next video of Unit 3, we're going to go into more detail about the various types of crystalline solids.